In the last video, we looked here at example number 4 to try to get a sense of how we could understand how to perform one of these large change of variables, the upgraded version of a U substitution. What we're going to take a look at now is a little bit more detail on how that works. When we take a look here at some general steps for performing the change in variables on a double integral, but also how is it that we could actually determine those red and blue regions that we're supposed to be working with if we haven't already dealt with them in a previous example. And that's what we saw in example 4 in the last video. So before we get there, let's take a look here quickly at a rough outline of the steps when we're performing a change in variables. Okay, so here's at least the first thing. We have to kind of be able to establish a transformation. In Calc 1, you had to establish what are you going to pick for u, right? You had to say, well, u is going to be sine of x, or u is going to be x squared, right? But here, I'm going to have to pick something for x and for y. I'm going to need something like that. And these formulas will be things that contain u's and v's. Okay. We'll oftentimes have to draw a picture of R, like what's the region that I'm integrating over? It's kind of like in Calc 1, I'd have to identify the interval that I'm integrating over. I want to make sure that my transformation is indeed a C1 transformation, and I'm definitely going to want to calculate its Jacobian. I know that I need that in order to perform the change of variables you see down here. Number 4, I'm going to use inequalities on R and the equations that determine my transformation, and I'm going to have to find the region S in the UV plane. This is the thing that we didn't have to do in the last video because we already knew what that region S looked like based on prior examples. And then the next thing that I would have to do is verify that the hypotheses are met to actually perform the change in variables. And then I can actually set up this hard integral and transform it into this easier integral over here. So oftentimes, as I state down here in the note, I'm not always going to write out all the details here for step 5. Some of the stuff will be fairly intuitive and we'll be able to just kind of mentally check it. So let's take a look at how we could begin to perform some of these steps as we work here through example number 5. So first, you have to just appreciate the complexity of the integral here in number 5, so we can want or actually understand the desire to perform a change of variables. So consider this integral here. Okay, already, even before I read what the region R is, if I'm just staring at that integral, look how messy that function is. I could start to see maybe almost immediately that that's going to be a really difficult function to integrate with respect to x. Because like, notice I have e, and in the power I have x over x. It would also therefore be like very complicated to integrate with respect to y, because I also have like y over y in that power. That's really, really messy. I mean, like if I had something instead like an e to the, say like x over 2, that's not too bad, right? Like that maybe I could integrate, I could do a simple u substitution with or something like that. If I have something like 2 over x, gosh, that definitely becomes difficult. And if I have something like an x plus a 2 over an x plus a 1, don't even bother. That starts getting so complicated so quickly. So we have a very difficult function here that we're attempting to work with. And on top of that, we also have a very awkward region R. We say here that we have a trapezoidal region that has the following vertices. Oh boy. All right, so we're going to go ahead here and start to try to work through this slowly. I'm going to kind of start here with step 1. I need to maybe think about a change in variables that might help me make this integral easier. Unfortunately, just like in Calc 1, when we make a substitution, like when you pick something for u in Calc 1, you can't really be sure at the outset that what you picked is going to work perfectly. Sometimes you had to actually do the substitution, change everything over, and then you would realize, ah, crap, this doesn't work very well. And so very unfortunately, we're going to have the same dilemma here. Now on this question, of course, I'm here to guide us, so hopefully we'll be able to make it through this one okay. But I'm going to think here, what would maybe be a change in variables that could possibly make this easier to integrate? That is, I need to find something that x could be equal to, and I need to find something that y could be equal to. Like, that would kind of be nice. But maybe before I'm able to do that, it might just be easier to think about a way that I could swap this around by thinking about maybe what could u and v be equal to. And you'll see why I do this in a moment. I want to go ahead and actually change this integral into something easier. And so I'm going to maybe propose the following. Maybe if I had u could just be equal to that top portion of the fraction. And therefore, I could let v be equal to the bottom portion of the fraction. If I did this, I could think that now I would have an integral that would look like an e, or would have a function in it of e to the power u over v. And I could ask the question, is that easy to integrate with respect to either of those variables? Well, you could think about that for a moment. Is that actually easy to integrate with respect to either of those two variables? And if so, which one? Well, what I would say is that it seems like it's easy to integrate with respect to the variable of u. It's not so easy to integrate with respect to the variable of v. V is in the denominator of the fraction, but u isn't. So I could always attempt to rewrite that as e 1 over v times u, and that I can maybe start to see, yeah, that's pretty easy to integrate with respect to u. If you're not fully seeing that yet, I would actually replace v or u with a number, just one of them, and see if you can evaluate the resulting integral, right? Or at least evaluate any, or find an antiderivative of that associated function. So if I've gone ahead here and I've established something that I think is going to be a good choice for u and v, notice that that doesn't really answer question 1, which says find something that x and y can be equal to. But of course, the moment that I have this, I could set up a system of equations and maybe solve for what x and y would be equal to. So if I have these two formulas, notice that if I took them and I added them together, I could get that u plus v is going to be equal to 2x, which of course then means that x is equal to a half of a u plus v. Okay, well, that's kind of great. If I have that x is equal to a half of a u plus v, I could also then go ahead and think about how I could solve for y. An easy way to do that, that doesn't involve too much messy algebra, would be to take the exact same equations and maybe just subtract them. This would get me u minus v is equal to 2y. So that would ultimately get me that y is a half of u minus v. And so I kind of have here a transformation that I think might work. We could have a transformation that takes in u's, v's, and it spits out the following for x and the following for y. This is, again, the hardest part of pretty much every change of variables, because I don't know that I was supposed to pick this for u and v. I have to experiment a little bit. And the best guide, of course, will be experience. Well, let's keep going here. Let's see what we can come up with for part B. Use the change of variables from A to evaluate the integral. Okay, so we've kind of already completed step 1 up above. And so step 2 was, can I draw a picture of the region? Okay, so I'll say here that we now draw a picture of R. So we were told that R is a trapezoid in the XY plane, and it had the following vertices. It had the vertices of 1, 0 and 2, 0, 1, 0, 2, 0, but also 0, -1 and 0, -2. So hopefully I can see that if I play connect the dots here, I can create a region that's in the shape of a trapezoid. So here's my region R. And my goal again is to take this region and understand how my transformation can create it. Okay, I'm going to go ahead though and quickly just define R in whatever ways are possible. In order to do that, again, what I mean is I want to find R as a region built of a bunch of points x, y, and I want to think about some of the restrictions that I have when talking about this region. Again, I could maybe see a couple quick things. First, I see here that x has to be greater than or equal to 0. I can see that y here has to be less than or equal to 0. That's guaranteed. But I can also see that the value of y has some additional restrictions on it. I kind of have to be below this one slant line and above this other slant line. You could probably do a little bit of work to confirm that these lines here have the following formulas. That line's y equals x minus 2, and this line here could be given by y equals x minus 1. So I can also put in here that y has to be beneath the x minus 1 line, but above the x minus 2 line. Okay, so like here's my region R. This is the region that I have. That completes step 2. For step 3, following the box above, I'd want to go to my transformation, and I'd want to confirm that it is indeed a C1 transformation. Let's quickly look. My transformation here has these values for x and y. If I take a look at the x formula, the partials of this are definitely continuous because this is a polynomial. Same thing over here. So I can say, for step 3, we see that t is a C1 transformation, and its Jacobian also needs to be calculated. So let's set that up. Its Jacobian should be crunched out the same way we've always crunched out Jacobians. Again, I'm going to take a look at my x formula and take its partials with respect to u. If I take the partial there with respect to u, I think I'm going to get a 1/2 v. Wait, would it be a 1/2 v? Quickly double check actually what all of the partials are going to be here, because oftentimes if we move too quickly, we'll write something down like this, and it'll definitely be wrong. I'd ask you right now, pause the video and see if you can actually write out what the actual partials are here, and see if you can calculate out the Jacobian. And when you hit play again, you'll see me working through the solution. All right, so here's the solution that I would come up with. I believe that the partial with respect to u is first going to be a 1/2, partial with respect to v is also 1/2, and then I get a positive 1/2 and a negative 1/2. When I set this up, this is going to give me negative 1/4 minus 1/4, which is going to be a negative 1/2. So here my Jacobian's a negative 1/2. Well, now I'm ready for step 4. In step 4, I want to try to understand what the region S is going to look like. So we now find the region S. Okay, so I need to try to go ahead and figure out what this region is going to look like. And this is the part that we didn't do in the previous video. It's not too difficult to do, but what I have to try to do is imagine converting what I have in my bounds here, and I have to imagine trying to convert those bounds or those restrictions into things that contain u's and v's. So I'm going to actually take a look at this region R up here and use this to try to help me. Okay, so here's what I have. I'm going to take a look at each one of these things individually and see how the transformations work. So I'll say, converting to u's and v's, we have that x minus 2 was supposed to be less than or equal to y. We saw that kind of up here in the box, or in the set notation up above. But what I can start to do here is imagine what would happen if I replace all of my x's with what x's are equal to. Remember that was 1/2 times u plus v. And if I replaced y with what it was equal to, that's 1/2 u minus v. So now I can have an inequality with u's and v's in it. I'd like to simplify that down as much as I possibly can. And what I'll notice that I get from this is you can see I'll get a 1/2 u on each side. And so I'll ultimately be left with just a 1/2 v minus a 2 should be less than or equal to a negative 1/2 v. Now, I can go ahead and simplify this a bit further. I can go ahead and say this is going to be the same thing as 1v being less than or equal to 2. And so I kind of have a new bound that I can work with for this region of S. So this is an important bound, and I'm going to mark that. Notice I have a couple other inequalities that I need to kind of change. I need to kind of change this other boundary, and I need to change the final two boundaries. Essentially, I'm changing all of these individual sides. I'm just dealing with them as inequalities. So let's take a look. I'm going to now convert one of the other sides. Well, one of the other sides was going to be where y had to be less than or equal to x minus 1. Again, if I replace y with what it's equal to, that's 1/2 u minus v, and that should be less than or equal to 1/2 u plus v minus 1. I want to simplify this down so I can find out what this looks like as simply as possible. And I think what I'll end up with at the end of the day, and you can double check my work, is that I end up with v being greater than or equal to 1. I would ask that you pause the video really quickly, make sure that you can actually confirm that that is indeed what you could simplify down to. Okay, I have two more inequalities that I need to go ahead and change. I need to change y being less than or equal to 0. Remember, that's that kind of that top edge that I have up here. Y's got to be less than 0. And when I change that over, I'll see here that I'm going to get a 1/2 a u minus a v less than or equal to 0. Interestingly, that kind of turns into a 1/2 u needs to be less than or equal to a 1/2 v. If I multiply both sides by a 2, I can see that really that just gives me u has to be less than or equal to v. All right, so that's another boundary. I just have one more side to change. The last side that I need to change was that x had to be greater than or equal to 0. That gives me a 1/2 u plus v greater than or equal to 0. That gives me a 1/2 u plus a 1/2 v is greater than or equal to 0. And overall, I think that gives me that u has to be greater than or equal to negative v. So if I was to take a look at all of these different inequalities that I have, I think I can write down what the region S looks like. S is a bunch of u comma v points with the following restrictions. I'll notice immediately that u has to be less than or equal to v, but greater than or equal to negative v. Those are kind of my last two blue inequalities there. But I can also see that v has to be less than or equal to 2, greater than or equal to 1. If I was to try to draw this out, I can see what that region S is going to look like. So here's my region S. This is going to be now existing in the UV plane. I'll start with that second inequality that says that I have to go from 1 to 2 in the V range. I'll then also think about the fact that U had to be less than V. So if I think about what the line U equals V would look like, that would be a line that kind of goes out like this. The line U equals negative V would be a line that goes out like this. And so I can start to see what begins to happen if I'm not allowed to go below this and I'm not allowed to go above this. I can see that there's a region, again, that begins to get formed. And it's this region that I have right here. I'll kind of erase all of the excess that I don't need there, and I find that I have a nice region of S. Strangely, it's still a trapezoid. It's a little bit frustrating that it's a trapezoid, but actually, it's not too terrible because the bounds on these variables are pretty nice. At least one of them deals with functions, but the other is dealing completely with constants. So now, for step 5, it's pretty easy to see here that the hypotheses for a change of variables have been met. And so I can immediately go to step 6. Step 6 is going to be actually doing the computation. So I had a double integral over R of this really nasty looking function. And what we said is that we wanted to convert this over region S. We thought about converting our function. Remember we said that x plus y would be the u, x minus y would be the v. We would have to put in the absolute value of our Jacobian. Do you remember what the Jacobian was? Now, if you look back up a bit, we should see that that Jacobian was a -1/2, and then we can put in our differentials. In this case, I'd have to think carefully. What would I want to integrate with respect to first? Take a look at the variable bounds. I should want to integrate with respect to u first, since that's got variables, and v last, since it just has nice numbers. So my bounds here would look like integrating from 1 to 2, from -v to v, e to the u over v, and then I'm going to have, I guess, just a 1/2 here. I'll squeeze that right in front, and then I have my du d. Notice this should actually be pretty easy to integrate. I took a hard integral and made it into something much, much easier. The antiderivative here, you could double check me, but I believe it's going to be a 1/2 v e to the u over v. And I just have to evaluate that from -v to v. This would turn into an integral from 1 to 2 of 1/2 v e to the 1 minus a 1/2 v e to the -1. When I go ahead and I evaluate this, I'll notice that, wow, actually, I could think about pulling the v out of this. I really have a 1/2 e to the first minus a 1/2 e to the -1 times a v. And so the antiderivative here becomes very, very simple. I'm just going to have a 1/2 constant v squared, and I evaluate from 1 to 2. When I plug in the value of 2, notice that I'm going to end up with 4 chopped in half, or actually if I pull out this 1/2, it could go even further, but I'll leave it in this way. I'll end up with 2 1/2 e to the first minus a 1/2 e to the -1 minus a 1/2 times a 1/2 e to the first minus a 1/2 e to the -1. And if I wanted to, I could try to clean this up. I think ultimately at the end of the day, I'm going to end up with 3/4 times e minus e to the -1, if I fully simplify things. As you can probably tell, doing this process of a full substitution is complicated. It takes a little while to get used to. There's a lot of different parts. Fortunately, the conversion part is the fairly simple portion. The hardest parts for you, the parts that will require your most practice, are going to be finding the region S and experimenting enough with enough problems to be able to guess what good values for u and v might actually be. There's nothing that I can do to tell you exactly how to do that, but your goal is ultimately to try to get down to something much, much easier to integrate. And so you can look at that by either getting an easy region, or maybe by thinking about what an easy integral function or a function that you're attempting to integrate would look like. Okay. In the examples that follow, we'll just go ahead and take a look here very, very briefly at some of the implications that we've already talked about, or some extensions, excuse me, that we will need to talk about. And I won't go through all the remaining examples in the videos to come, but I will talk about at least some of the following extensions that we'll need.